Hi folks, Mr. Long here, and this is an AP Calculus screencast. This is a challenging question where tables of values are used to solve the problem. It also involves related rates and tangent lines. So it's in the first fundamental theorem. So there's a lot of different things in this question. It's a particularly good one. Okay, so it's 2007 question 5, and what I've done is cut and pasted out the key elements of it, and also set it up so it's a little bit more user-friendly. So the first question is estimate the radius of the balloon when t equals 5.4 seconds using the tangent line approximation at t equals 5. Is your estimate greater or less than the true value? Give a reason for your answer. So we have in front of us this question. We've got this table of values which represents the derivative for rate of change, right? And we've got some important information here. We've got the volume of a sphere is listed. We've got there's lots of different things that are listed that we can work with, and so we can work with the volume formula. We know that r is radius in feet, t is time in minutes. We know it's twice differentiable and it's concave down. That's the graph of r, not r prime. And it gives us a radius at 30 centimeters when t equals 5 minutes. So the first thing is you look at the table, and what I really would have you focus in on is the fact that it says r of t, or r prime of t rather. So that's a rate. Anyway, so it says that they want to estimate the radius of the balloon when t equals 5.4, and then at t equals 5. So we need to keep a tangent line approximation, or create a tangent line approximation at t equals 5. Okay? This right here represents the tangent line approximation. Right here, that's what we use for a tangent line approximation. So we use f prime at t, we use or f prime at a, we use x minus a, and we use f at a. So we need a variety of things to be able to do this. So the first thing I would do is say, okay, a has to equal 5 in this case, okay, because it says make the tangent at 5. Well, we know then what's r at a. Well, r at a is 2, and that comes from the fact that at 5 minutes, r prime of t is 2. And now we need to know, oh whoops, that's r prime at a, and then we also need to know, of course, what r of 2 is. And r of 2 is, r of 5, and r of 5 is given as 30, right, in the question, okay? So we need those three things. We need f prime of a, and we need a, and we need f at a. So I think we've got that done. So there's our a value of 5, r prime at a, which is r prime at 5. That's given us 2 in the table. And right in the question, it gives us that r at 5 is 30. So I'm going to write this down in terms of r and a. So y of the tangent equals r prime at 5 times by t minus 5, because it's x minus a, t minus a, plus r at 5. And so I can substitute those values in. R prime at 5 rather, is 2. T minus 5 plus r of 5 is given as 30. And now what we can do is we can substitute t right there in as 5.4. So it's going to equal 2 times 5.4 minus 5 plus 30. 5.4 minus 5 is 0.4. 0.4 times this 2 is 0.8, and that gives us 30.8. Okay, and so that is the tangent line approximation. So the way we should say that, though, is that r at 5 equals 30.8 centimeters using the tangent line approximation. Okay, you want to say something like that. Okay, that should be your conclusion. Now, one of the things that's in this question, I really like this part of the question, is your estimate greater than or less than the true value? Give a reason for your answer. Remember that there are only four characteristic shapes of curves. So we have to find out if this is an overestimate or an underestimate. And the four characteristic shapes of curves are right here. So if f prime is greater than 0, so if the function is increasing, it can increase and smile, or be concave up. It can increase and frown, concave down. It can decrease and smile, so f prime is positive, f double prime is negative, and it can decrease and frown. So in other words, f prime is both negative, f prime and f double prime are both negative. So what is the shape of our curve? Well, you know here it's given that all of the r prime values are positive. So this function is always increasing, the r function that is. The derivative is always positive, so the original function is always increasing. But it also gives us that, right in the question, that it's concave down. So we have to find, and concave down means that the second derivative is negative. So which of these curves is always increasing? So in this row, the curves are always increasing. Well, which one of them is concave down? Well, it's going to be obviously that one there. So we know that's the general shape of our curve. So if we look at this, that's the general shape of our curve. So the curve looks like this, right? And so that means that any tangent line drawn on that curve is above the original function. That means that it will overestimate the r values. So you need to say in your solution, needs to say something to the effect, since the curve is concave down and increasing, the tangent line is above the curve. And the r values predicted by the tangent will be greater than the r values from the original function. Okay, folks? So you might want to repeat that and listen to that again, but it's above the curve. The tangent line is always above the curve. All right, let's move on to B then. Okay, so we need to do, in part B it says find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate units of measure. All right, so there's some really important ideas here. We've got a volume formula, but we've got some of the other big things that's going on here. We know that we have three variables, v, r, and t. Well, that means we need related rates. Okay, we've got a radius is a function of time, but volume is a function of radius, right? So we have v of r of t. So we have to use the chain rule and use related rates. Okay, so let's, first things first, it says find the rate of change of the volume with respect to time. So we need to convert that question into language, into calculus-based language. So they want us to find dv by dt. Okay, that's what the goal is. So we need to get dv by dt using the equation that's given. So what is the derivative of that? The time-based derivative will be dv over dt equals 4/3 pi, and then the derivative of r cubed is 3r squared, but I have to write dr by dt. 3's divide out, and I'm left with, dv by dt equals 4 pi r squared dr by dt. And this is I'm supposed to do this at when t equals 5. Well, when t equals 5, we know that dr by dt is 2.0, and we know that the radius is 30. Okay, so all I need to do is do this, and I'm doing it when t equals 5. So when t equals 5, we've got 4 pi times by r. r is 30 squared, dr by dt, which is given as 2. And that's going to work out to 30 squared is 900. 900 times 2 is 1800 times 4. 18 and 18 is 36. That's 7200 pi, I believe. Yeah, so that equals 7,200 pi, and that is in feet cubed per minute. Okay, and that's dV by dt when t equals 5. Okay, and that's all. You just have to make sure you have units. It's really important to get those units in there. Feet cubed per minute. And again, you can pause and rewind this at any point in time. So let's move to the next. R is radius in feet and time in minutes. So in this case, what we need to do is do a right Riemann sum. So a right Riemann sum. Well, how do we do that? Well, a right Riemann sum with 5 subintervals. So if I'm going to do this, and I'm just going to make this a little bit bigger so I can see it. So I want to get area under the curve, a right Riemann sum. And so I know this is 5.7, and then this is 4, and this is of a y value of 2, and then a y value of 1.2, and then a y value of 0.6, and then a y value of 0.5. And I'm going to be making rectangles. So if there's 1, 2, 3, 4, 5, 6, I can make 5 rectangles. So my rectangles are going to go like so, like so, like so, and so on. And it's a right Riemann sum. So if I'm going to do a right Riemann sum, it says do the integral from 0 to 12 r prime of t dt. So what will that look like if it's a right sum? Well, I know that in a right sum, I look at each rectangle and I use the y value on the right side. I use the y value on the right side. And in the first rectangle, which goes from 0 to 2, I know that that rectangle is 2 wide, and then the y value on the right side of it is 4. So the height is 4 multiplied by a width of 2 plus, and then I go to the second rectangle. Okay, so my second rectangle, right from here to here. And I know that the right y value, the right y value is 2, and the width of that rectangle, it goes from 2 to 5, so that's 3. Okay, and that's the first 2 rectangles. Then I need to add on the third rectangle, and the third rectangle goes from x equals 5 or t equals 5 to t equals 7. And the right hand side of that, the height is 1.2. So it's going to be 1.2. And the width of that goes from 5 to 7. That's 2. And then we're going to add on, I go to my third rectangle. And the third rectangle goes from 5 to 7. Whoops, sorry, 7 to 11. Wait a second. So the first one goes 0 to 2. 2 to 5, 5 to 7, 7 to 11. Now 7 to 11, on the right hand side, it is 0.6 tall. So 0.6 multiplied by a width of 4. And then the last rectangle, that's 4, and I have one more rectangle to do. And the last rectangle is plus. Now this one is, how big is this rectangle? This rectangle is 0.5 tall, right? At 12, it's 0.5 tall, and it's only 1 wide. So from 11 to 12. So the height is 0.5. The y value is 0.5, so 0.5 times by 1. And if I get the area of all 5 of those rectangles, then I get an answer of integral from 0 to 12 r prime of t dt equals, I have to figure out those and get the accumulation of that area. And the total of that is 19.3. Sorry, I'm moving around on my chair here. 19.3. And if I look at the units on that, it's 19.3. R prime is feet per minute. And then on the x-axis, it's minutes. So it's minutes times feet per minute, which just gives me feet. So, and then it says, so that's the integral that they asked you to find. And then they say, what does that mean? Well, we know from the first fundamental theorem that the integral of 0 to 12 r prime at t dt equals r at 12 minus r at 0. Now, it doesn't give me r and 12 and r at 0. It just tells me how much the radius changed by. From 0 minutes to 12 minutes. Okay, and so that, folks, is that's your question. That is your solution. All right, let's try one more. Okay, let's do part D. So part D is asking about whether your approximation in the last your approximation of area under the curve was an overestimate or an underestimate. So what's meant by this question is, if you look right here at this integral, that integral, they're saying that is the true value underneath of the area under the curve. And what we did, because we did a right-sided Riemann sum, we just did an estimate, an approximation. So what we need to do is consider what the graph of the derivative looks like. So if you remember back to part A, we had to imagine what the graph of the original function looked like. Well, now we have to imagine what the graph of the derivative looks like. And I have to tell you, it's easy to make a mistake here. I know when I first looked at this question, I kept in my mind, I was thinking what the original function looked like, because I had done that earlier with the tangent. So what does the original curve look like? Not the original curve, folks, sorry, the derivative. So we know the derivative looks like this, right? It's decreasing, but it's above the y-axis. That's the graph of r prime. And now we need to take the area under the curve. So as we're doing this, and we're getting these right-sided intervals, and I have to just undo a couple of things here. You know what, I'm just going to go work that down a little bit further down. I didn't draw that quite correctly. Okay, so there is our curve, and I'm doing a right Riemann sum. So that means I draw my boxes, and to get the height of each rectangle, I go to the right side of the rectangle. There, and so on. So if you look at that total area, because it's based on, the y value is based on the right side of the rectangle, will that be an underestimate or an overestimate? Well, clearly, since there's extra space left over that's not shaded in under the curve, we have underrepresented our area. So our estimate is less than the true value. Okay, it's less. And then our reason would be that our function is decreasing and concave up. Okay, it's decreasing and concave up. All right, now that's a really tough question. That's one of the tougher AP problems that I've worked through. What I would encourage you to do is to go back over and take a look at this and watch it again, pause it, think through it. There are so many aspects of calculus in this question. There is the first fundamental theorem. There is the tangent line. There is concavity, impact of concavity on whether a tangent underestimates or overestimates, and then the impact of concavity and slope on whether the area under the curve is underrepresented or overrepresented. There's also the chain rule that's used and a related rate, time-based derivatives. So I think this is a particularly good question, but you also have to remember that this is really tough, and I'm sure the average score on something like this would be maybe between 2.5 and 3.5 marks out of 9. But take a look at it. I think you could probably easily get a 5 or 6 points on this on test day. Hopefully that helped.